With molecular compounds, we frequently talk about bond enthalpies, which is the bond energy, potential energy that is stored within a covalent bond. With ionic compounds, we frequently talk about a quantity known as the lattice energy. And so if you think about an ionic compound, remember that you have a certain ratio of positive cations to negative anions. And rather than having finite individual molecules like we have with covalent compounds, your ionic compounds form more of a network, and it continues on in all different directions in that ratio. And so the lattice energy refers to the energy that's going to be involved between the ions of that ionic compound that they form. Now, it can be measured in a couple of different ways. Right? It can be described as the energy that's released when ions of the elements that are making up the solid in their gaseous state, okay, come together. Remember, anytime you have bond formation, that involves a release of energy. And so that would be a negative value. And so your enthalpy would be a negative when the bond is formed. You can also sometimes see lattice energy described as the energy required to take an ionic solid and separate it into the gaseous ions of the component elements that make it up. And so in this case, you're basically doing the reverse of that original process. So here your enthalpy would be a positive value, but numerically it's going to be the same quantity of energy. Now, to determine or to infer how much energy is going to be involved, you have to consider two things. First of all is the charge of the ions that are involved. The bigger the charge, all right, if we look at Coulomb's law, the amount of attractive force is going to be proportional to the product of the two charges, that's your Q terms, divided by the distance between those two charges squared. Okay, so as you can imagine with the values of the charge, the magnitude of the charge, the bigger the numerator is going to be, therefore the bigger the attractive force. Conversely, the size of the ions involved is also going to have an effect on the magnitude, and given that the distance between the ions is in the denominator and it's squared, how big the ions are is going to play directly into what is the length of that internuclear distance. And so the bigger the ions are, the bigger the distance. Well, as your D term increases, especially being squared, that's going to have a diminishing effect on the attractive force. So if we take a look at these two data sets here, okay, in the data set A, we're comparing some chlorides and looking at their lattice energy. In data set B, we've got a mix of some chlorides and some oxides and their lattice energies. So if we want to determine which data set can be used to analyze the effect of the size of ions, right, we'd want to pick a data set where one of the ions is being held constant. So we can look at the other ion and determine which, as that changes, what's happening to the lattice energy. And so data set A, right, where all of them are chlorides. So the only variable that's changing is which alkali metal, lithium, sodium, potassium, rubidium, or cesium. And so we can see that as we go down the alkali metal column, right, the size is getting larger because you have more electrons. And so therefore, if the size of the ion is getting larger, then the distance is becoming greater, and therefore there's less attractive force, and hence why the lattice energy is decreasing. If we take a look then at ion charge, okay, sodium chlorine, sodium is a +1, chloride's a -1. Magnesium chlorides, magnesium's +2, chloride's -1. So there you can see, the magnitude of the charge on the cation is doubled. We see a dramatic increase in the lattice energy. Okay, here we have +1 for sodium, -2 for oxygen. Again, it's a 1 and 2 combination. It's just flip-flop between the cation and the anion, and notice there's not a huge difference in the lattice energy. So it doesn't really matter which ion has which number, it's the combination of the two. Magnesium oxide, +2, -2, now we see another big jump in lattice energy, and aluminum oxide, where we have a +3 and a -2, all right, we get a really big jump in the lattice energy. So set B would be, is illustrating for us the effect of the effective ion charge on lattice energy. So let's take a look at that, and using that in each of these pairs, determine which one's going to have the higher lattice energy, and we should be able to justify it. Well, in both of these first ones, we have magnesium, magnesium oxide, magnesium chloride. The first thing we want to think about is the charges. That's the predominant one. And so magnesium's a +2, oxygen's a -2, so we've got 2 and 2. Chloride is a -1, so here we have a 2 and a 1. So magnesium oxide would have the higher lattice energy based on ion charges. The next row, magnesium chloride and magnesium fluoride. Again, they're both magnesium compounds. Magnesium's +2. Chlorine and fluorine are both halogens, so they both have a -1 charge. So there's no difference in the ion charges. So we need to think about the size of those ions. And fluoride ions are smaller than chloride ions, therefore it's going to be a smaller internuclear distance, and therefore a stronger lattice energy. Magnesium oxide and calcium oxide. Magnesium and calcium are both alkaline earth metals. They have a +2 charge. Oxygen is a -2. So once again, the charges match, +2 and -2 for both. And so we have to look at the difference in the size of the ions. And since oxygen is common to both, we look at magnesium versus calcium. Magnesium is smaller than calcium is, so magnesium oxide would have the higher lattice energy. And then finally, aluminum chloride and aluminum oxide. Start by looking at the charges. Aluminum's +3, chlorine being halogen is -1, oxygen is a -2. So Al2O3, aluminum oxide, is going to have the higher lattice energy because of ion charges. So here we have a list of different ionic compounds and a list of lattice energies, and our job is to determine which compound is going to match with which lattice energy. So we know that the highest lattice energies are going to be associated with ionic compounds that tend to have higher charge combinations and smaller ions. So if we start with the charges, lithium fluoride, that's going to be +1, -1. Lithium and oxide, that's going to be +1 and -2. Potassium fluoride, +1, -1. Potassium bromide, +1, -1. Potassium oxide, +1, -2. So in terms of charge, our two oxide compounds are going to be vying for these top lattice energies. So because they both have oxide in common, we look to the size of the cation, and lithium is the smaller of the two. So that means that lithium oxide, by a combination of its charge distribution and also the size of the cation, that's going to be associated with the highest of our lattice energies, followed by the potassium oxide. So now we have these three remaining lattice energies in three compounds. And so they all have +1, -1 for their charges, so we are left with the ion sizes as our determining factors. All right, and so if we think about these, lithium and fluoride are both at the top of their respective columns, so they're going to have the smallest radii. Potassium fluoride, potassium is going to be a little bit bigger than lithium, and then down for this third one, bromine or bromide ion is going to be larger than fluoride. So the smallest ions are going to have the highest lattice energy because they're going to be closer together. So lithium fluoride would be next, followed by potassium fluoride because you still have that small fluoride ion. And finally, the potassium bromide, bromide being larger than fluoride, would bring you to this last lattice energy.